Everyone,
Hello.
welcome to ITS 350. So let's get started. Today, I'm not going to be presenting that much, right? And instead, today is a lab, so I will leave it open. If you guys have questions, I'm going to just answer questions if you have them, and also assign the new lab, which is the PKIa lab. And we will be doing this lab. It's going to be due 1 week from today. So at this point, we've done 3 labs. If you remember, we had the secret key lab that was due last Thursday. We have the hash integrity lab that's due tonight. And then now I'm assigning public key lab, this one, PKIa. So I'll explain what we need to do. So I'll explain what the public key lab entails for this week. This is a big lab, this document. And so what I'm doing is I'm breaking it up into 2 parts, what I'm calling basically PKIa and PKIb. And some of the coding assignments that we're doing, I've changed a little bit from the PDF, but I'll explain all of that in the video and, post it on the link later on. Okay, so there's 2 PDFs that I posted on GitHub. Oh, sorry, not on GitHub, on Brightspace. They're pretty much the same document, I gather, is just, the updated one. So this is the old version of PKI, and you can see here, so it's got some of the information, but it's really pretty much the same. Task 3.1, become a certificate authority. And then task 2, create a certificate. Task 3, use PKI for websites. And then that's all we're going to do for this one. For this PKIa lab, I mean, just those 3 problems, which are actually not, they're dependent on each other. It takes a little while. And then PKIb next week will be task 5, performance comparison. And task 6, which is create a digital signature. We haven't covered digital signatures yet, so I'll be covering that sometime in the future. And so once we have that, we'll be able to get into this. Okay, so as I said, from this lab, PKIa, you're only responsible this week for 3.1, 3.2, and 3.3. Use PKI for websites. But I will specify that as well in the, when I create the link on Brightspace for the homework assignment. If we take a look at the other one, the other version, public key infrastructure PKI, which is the more updated version of this same lab. Let's take a look at it. You can see it's similar. Task 1, becoming a certificate authority. Certificate authority is there. Creating a certificate authority for PKI Lab 2020. You can see that there. And then deploying certificates in an HTTPS server. And that looks to be pretty much the same as well. Getting your browser to accept it, that's the same instructions, testing it, and that's it. So we're going to be doing those. Task 4, deploying certificate in an Apache-based HTTPS website. That's something that we're not going to do for this lab. I cover this in 450 and other courses anyway, so we may not get to it at this time. And then we'll see. So we may not do everything in this document because we have the supplement of the other one, which is really, I want to cover, I believe that covering the performance is very, very important, and also covering the digital signature. Okay, so basically for the first three problems, I'm assuming both documents are the same. If anything, it's possible that the newest lab has a few new statements in there of little errors or clarifications that. So what I would suggest is, can you guys see the PDF? Still see the PDF?
Yeah, I can see the crypto PKI one, and then PKI seed is in the alternate, also the alternate tab.
Okay, so there. Okay, yeah. So probably just read both. Okay, so it doesn't hurt to read these. Remember, these also go with the chapter in the book. I already gave you the chapter. I don't remember offhand right now, but I'm sure I did that on Tuesday. So that's pretty much what we have to do. I will of course explain this. We've already covered asymmetric encryption. This is about asymmetric encryption, but as you might already have identified or picked up on it, public key infrastructure PKI, right? So public key, that basically refers to public and private key. And so I gave that the underlying framework or methodology, if you want to call it that, on Tuesday, theory, and today I'm just going to explain the lab. So it's like we're using those ideas, but in a way that we don't necessarily have to write any code in this one. It's really, we're just going to use, again, as you might imagine, OpenSSL to create our key. So somebody asked a question. So again, I will repeat, you should be looking at two PDFs, Crypto PKI on one tab, PKI seed on the other one. Both of them, the first three problems are almost exactly the same. So read either one, read both. You'll be rereading things. They're just, a newer version of, one is an older version, is a newer version. So just read through them. These labs, both of them, they're the same. As far as task 1, becoming a certificate authority. Task 2, creating a certificate. And task 3, deploying certificate in an HTTPS web server. So you're going to do these 3 problems, and only these 3 problems for this one lab assignment. Okay, is that clear for everyone, guys? That's why I'm calling it PKIa. Okay, great. So I'm calling it PKIa. I will again say in the link, the attached PDFs, do the first, this one, and this one, and only that. And you'll have a week. It's due a week from today. Okay, and then next week we're going to do PKIb, which will be a combination. Yeah, exactly. So they're the same files. Only one is a newer version of the other one. It's got, so it might have, whereas probably if you follow the old one, there might be things that are a little bit more confusing, which have already been corrected in the newer one, but just read both and, get into the habit. The more you read, the more you'll learn. So go ahead and read through them. It should be a very eye-opening lab. I think you haven't really, seen something like this yet. Okay, and so you'll see how important all of this is. All right, so I will just give the basic layout of what this lab is. So let me switch over to the whiteboard. Okay, so you should be looking at the whiteboard now. So basically, we looked at asymmetric encryption on Tuesday. And then this PKI lab, PKIa, is a framework that implements the idea of public and private keys for the problem of the client-server architecture. You've got a client and a server. And you want to establish a secure connection. But if you remember, the problem that we identified on Tuesday that we can't just use symmetric encryption, right? What was the problem with that, with just using symmetric encryption?
How do you tell the other side your key?
Your key,
Security.
exactly. If you're, if you're going from your laptop to Amazon, you can't just meet outside of the channel. You have to exchange the key in a secure way. So that's where symmetric key comes in, and you can think of it as, okay, now symmetric key will create a secure channel, and then using that secure channel, you send the secret key to the other side, and then you can start the encryption process. So that whole idea in a client-server architecture is captured by this lab, PKIa, which is problems 1, 2, and 3. Okay, now on the client side, you're basically going to be using the browser. The browser, Mozilla Firefox, is going to be your software. Okay, so the browsers, are very important for security, right? You have to have a good browser because, the security of your everything is, guaranteed by the browser itself. So the browser is the one that's going to initiate a secure connection with the server. The server on this side would have something like Apache or something, some service like that that's secure. And so it's got a port open, and then this will initiate the communication and do the entire process. Okay? The exchange of the keys, the exchange of the communication, all of that. So your browser on your computer will be involved. Now you might ask yourself, so where is this server? Because, you don't have access to a server, right? We're not going to go into the cloud or anything like that. So instead, to complete this lab, there are 2 ways that you can do it. You can start 2 VMs, VM1, VM2, and then the browser is on one VM, and then on the other VM, you're going to see instructions in the PDF that say run a script. You're going to run a specific little program, and that little program, when it's running, it's going to basically simulate that it is a type of service like a web server. And then it'll make the lab very easy because now you will be simulating this Apache on here. So you'll have that, and then you'll have the browser, and then you can establish, do the whole process of communication. You can do it that way, that's perfectly fine. Or you can just do everything in one single VM. So for those of you that maybe have limited RAM on your memory, have trouble starting, two VMs, you can just do it on one VM. It's really the same thing because in a VM, you can open 2 terminals, right? So we have, terminal 1, terminal 2. So you have 2 terminals in there. And then what you're gonna do is that, on one terminal, you're going to run the script, right? So you run script, and then the process is gonna start. That process would start on your same machine. And then for the other part, you can just go ahead and open a browser. And so you basically have 2 separate processes on the same machine versus here, where you would have one process on one VM, one process on another VM. Here you will have one process and another process, but both on the same VM. It's really the same thing. The only thing that would change is that the IP would be the same here. And then here the IP, would be IP1, and then on this other end, it would be IP2. Okay? That's the only difference. So how you do it, perfectly, either way is fine. Are there any questions about that?
I don't think so.
All right, good. So that seems like that's clear. This lab, so some recommendations about this lab, okay? Okay, let's see, I have some chat. Always takes me a while to get to this chat. Okay, let's see. Which one do you, okay. I do not prefer either one. It makes no real difference. I mean, for those of you that really like, you know, a challenge, do the other one. It's not harder, it's just, you know, you have 2 VMs. It's more correct, I guess, right? Because you wouldn't usually, you know, we're simulating going to your bank, going to Netflix, going to Amazon, going to Facebook, you know, all those things. So it would be from one server to the other. That's a good question. So some students want to know if they could do this from their Windows physical machine to the VM. So in theory, all you have to do is modify your browser. So if you have, I do recommend that you do this with Mozilla Firefox because the instructions are provided for Mozilla. So if you have Edge or you have Chrome, you know, that's not the instructions. Technically speaking, on the client, you really, I believe, only need to change the browser. So you might want to venture and do that. It's up to you. But you will have to create all the keys and everything on Linux, right? Because we're using OpenSSL. So that's one thing you will have to do. All right, so I kind of laid this out. So the best way to go about this lab is I'm just going to read through the first 3 problems to refresh my memory on the requirements, and then that way I can explain things. Now, one thing I will say about this lab, and it's that this lab is not like the other labs. This one requires a little bit more concentration. It's a little bit harder because there's a lot more steps that need to be accomplished in a sequence. You know, so one of the key concepts is that we are going to be talking about certificate authorities. Okay, certificate authorities, and you know that's sort of a new concept, but it's a new concept of applying what we learned on Tuesday. So first of all, who can tell me what is a certificate authority? What do you know about certificate authorities?
Isn't it it doesn't kind of just verify that the owner or the integrity of, like, say, a website or a connection basically is just saying, hey, this is legitimate?
Yep, that's true. What's an example of one company that does certificate authority?
Well, from what I read in the doc, I know VeriSign is one.
Is one. I believe GoDaddy also does that. And there's several. I'm sure Google and the big companies all have their own. So how do you think they do it? How do you think VeriSign does? You know, how do they do what you just said? How do they? You said they authenticate that whoever owns that website is telling the truth. So how do they do that? Do you think? Any suggestions? No ideas? Well, as it turns out, they use what we learned, what Bob and Alice were doing on Tuesday, right? They were, you know, Alice was signing with something that everyone could decrypt, but only she could have. And so by signing it in such a way, it meant that that entity had verified it. Do you see that? So that's sort of the idea, but we will talk a little bit more about certificate authority as we go forward. Okay, so before I get actually into discussions of certificate authorities, let's just go over the lab itself. So I want to make sure I assign the lab before I go into, because I may just want to save the theory for next Tuesday. So let's go ahead and give you enough time to work today to work on the lab. Let me I need to share the PDF. All right, so you should be seeing now the Public Key Infrastructure PKI Lab. All right, so let's go through that. The public key cryptography is the foundation of today's secure communication, as you know. It might be subject to things like man-in-the-middle attacks when one side of communication sends its public key to the other side. The fundamental problem is that there is no easy way to verify the ownership of a public key, right? Given a public key and its claimed owner information, how do we ensure that the public key is indeed owned by the claimed owner? The public key infrastructure PKI is a practical solution to this problem. Right, so that was the same problem that we had on Tuesday, right? We received a confidential message from Alice to Bob, but in a box. But then how do we know that it was actually Alice, right? So we introduced this idea of Alice using her private key to further encrypt the message, okay? And so this one, certificate authority, just takes that a little bit further, right? It takes it a little bit, it centralizes it a little bit as well. So the learning objective of this lab is for students to gain firsthand experience on PKI. Seed labs have a series of labs and this one focuses on PKI. By doing the task in this lab, students should be able to gain a better understanding of how PKI works. And in particular, how PKI is used to protect the web and, to provide more security. Moreover, students will be able to understand the root of the trust in the public key infrastructure and what problems will arise if the root trust is broken, right? And that's sort of the new thing that I'm introducing now, because, as you probably have gathered now with all cryptography, it always just, gets more complicated, right? So we took some primitives, we build a system, and now those primitives, we're going to add even more, and it, gets more, so that we can achieve more goals. Okay, so that's the objective. So in this lab, we will explore public key infrastructure. We will explore certificate authority and the root CA, self-signed certificates, which is what you will be doing today. And then HTTP and HTTPS, that type of encryption. We're not going to look at man-in-the-middle attacks, so I'm not planning on covering that in this lab. All right, and then as you've gathered already, right? So chapter 23 of the book covers that. TLS, you don't have to worry about that. I usually cover this as it relates to VPNs, so we don't have to cover that now. Yeah, so this is probably, now they broke this lab into two parts, is what I see now. So PKIb, what I usually had done in the past is I broke the lab into two, and they did also the same thing. They broke it now into two. So we'll probably, when we do PKIb, remind me to take a look at this one, or you can just already download it from the Seed Labs, and just be aware that that will probably be your guide for another guide for PKIb. But I'll probably just post it on Seed Labs, or on the Brightspace, sorry. Okay, the VM, you know about that. Then as far as the instructions, right, all you have to do is read this carefully and follow the steps. You'll have to follow these steps. Here, you have to, in your computer, in the Linux computer, you'll have to create a directory, and you'll have to move some files or create some files. Okay, so just read the instructions carefully. You have to do all of this. Okay. And then you're going to have the instructions to create certificates, public keys, and private keys. So one of the things that you do in this lab is that you become your own VeriSign. So that's why I asked you at the beginning, what's one company? And what that means is you become your own certificate authority. So you can, via OpenSSL, basically become your own certificate authority. And then you can sign your own certificates. So you're going to end up being like your own VeriSign. You're going to create a website, and then you're going to sign that website's keys. Now, the trick for this to work is that the browser usually contains a list of well-known certificate authorities, things that are trusted, right? Because they have to be trusted. Like VeriSign is trusted, and so Mozilla and all those companies, you know, they have agreements, legal agreements with all these certificate authorities to have them in their browser. Okay, and what you're going to do now is, because you're an administrator on your own computer, the browser also allows you as an administrator to add new certificate authorities as you see fit, but these are now only local to you. So what's going to end up happening in this lab is that to your own browser, you're going to add the keys of the certificate authority that you created. So you became your own certificate authority, and you're going to plug in those keys in the browser itself. So therefore, when you sign, you know, a server's website keys, right, with your own key, and then from the browser, you initiate communication with that server. When you're doing the authentication on the browser is going to say, hey, this has been signed. This key I just got from the server has been signed, but it's not VeriSign. So I wonder, are there other certificate authorities in my list that I can trust? And so it's going to search. If you haven't added your own certificate authority to the browser, it's going to say, nope, I don't know this, so this is insecure. But after you add the certificate authority to your browser will say, oh, here it is. It's a self-signed certificate authority, so okay, I can trust it, and then I'm going to proceed. Does that make sense, guys?
Yeah.
Yeah, and that's it. I mean, that's the basic idea of this whole lab. Everything else is just creating keys and following the steps. But the one process you have to understand really is that, okay? So as we continue here now, creating a certificate for PKILab2020.com. So as you can see, this is basically like saying, I'm going to Amazon.com and I'm going to buy some things. Okay, but I need to initiate a secure client server communication. So in this lab, you're going to create this called PKILab2020.com. That's the Amazon or your bank being simulated, and you're going to create signed certificates for that website. So you can, you know, as I said, follow the instructions, generate public-private key pair, generate certificate signing requests, generating the certificates, and all of that. And then deploying the certificate, you'll follow these instructions over here, configuring the web server, and so on. And then here are the instructions, what I was saying, of adding things into the browser itself. So you're going to go into Firefox. You're going to copy a file, basically, a file that identifies something as a certificate authority, and it gives it the keys. And then you're just going to test it. Now, when you test it, make sure, usually when you go to an insecure website, what happens is the browser says, hey, I don't trust this. Are you sure you want to proceed? If so, you add an exception. But that's not the way that you prove that this lab worked, okay? I want to stress that. This is very important. If you get to the browser and it says that the only way you can get in is by adding an exception, then you did not do the lab correctly. Instead, it should be seamless, right? That you go in, and then when you make the connection, because you've done everything right and you have the keys of the certificate authority in your browser, the browser will recognize everything and will let you in, okay? So just be aware of that. That's a pretty important, you know, result that you need to have. Okay, and that's basically it. We won't do, for this PKIa, you'll stop at this point, so you won't do task 4. Now, if you look at the PDF, the old PDF, you can see it's pretty much the same. pretty much the same. The learning objective of this lab is for students to get familiar with the concept of public key encryption, public key infrastructure, PKI. After finishing this lab, students should be able to gain firsthand experience on public key encryption, digital signature, public key certificate, certificate authority, and all of that, right? So that's kind of where it's going. So, but really the focus of this is just certificate authority for this lab. So, does this make sense? Are there any questions? All right, so there's no scripting in this PKIa. I think it's pretty much a tutorial for this one. Just one recommendation is make sure you read everything carefully, because what usually happens is that students miss something and then it doesn't work. You know, this is the kind of thing where it's like Linux configuration almost, like a sysadmin type of lab, and if you do it wrong, unfortunately, sometimes you have to restart the whole thing again. It's the only solution. All right, so now let me just go a little bit into the slides to discuss certificate authority, or not slides, sorry, the whiteboard, and then after that, I will just leave the lab open for questions, okay, for questions. So certificate authority, and it's always good to think of like VeriSign or some, you know, some company like that. All right, so they're just a company. And what happens is you have the client, and then you have the server, right? So you have the client and the server. And so VeriSign from the browser itself is, the browser is the software that initiates through something here, you know, let's say the web server software, and it wants to initiate a connection. So this has some keys, public and private key, right? And you have some public and private key. So what your browser will do is, so we've already established, right? The browser has the public and private, and it also has the block or the symmetric key, the block cipher key, which is, let's say, for AES. So it's going to use this key for confidentiality. So for confidentiality, you're going to actually use this key to establish the secure channel. But the problem is you have to exchange this key. So right now, the channel is insecure. So you can't just send this key like that, because then Zelda will intercept it, right? So you can't do that. So then what did we say we would do in this scenario? Let's think about it. What would you do then? And I'm just going to say here, client, pub private, and server, pub private. So what do you think you do? Guys, to exchange the key?
You could encrypt it using the client's private key, so that way the web server can decrypt it with the client's public key, ensuring that it is only client that is the one that did it.
Right, and what you're saying is pretty good, except it's more important in a sense that we do that for the server and not the client, because this is the bank, right? So the stakes are higher on the client, you, right? So Bob, and your money. So actually you want to make sure that before you go to this web server, right, that they are indeed who they say they are, because you're about to put in your bank account or your credit card information, and they could steal all your money, right? So your goal is to use the secret key for confidentiality, but you need to exchange it securely. So how do you think you could do that? So the same thing you said, but just say it now in terms of the server.
The message could be encrypted with the server's private key, and then the client would be decrypting it with the server's public key, basically ensuring that it could have only been the server side or the bank side that could have encrypted it.
Right. So what are we sending? What's this message that you speak of?
It could be anything. It could be when your bank account records. It could be your regular account information.
But actually, all of that encryption will be done through symmetric key encryption in AES, block cipher. So really, all you want to negotiate via this mechanism of asymmetric encryption is the key. Does that make sense?
Yeah.
So this key, right? I'm talking about this one, the symmetric key. They need to exchange. So maybe it was confusing that I wrote it on this side. I should have written it over here, I guess, that the AES block cipher key, right, will come from, let's say, the browser. So once they both have the key, they can easily communicate, right? But they need to exchange the key. So then you said, so now let's think about it. The server has the key and needs to send it, right? So the key is, let's say here, key. It's about to leave. So what needs to happen?
I mean, it needs to be encrypted.
Okay, with what? So what now? With
The server's private.
Yeah, server's private, right? Okay. And then when that arrives over here, what does the client do for Bob? It uses the server's
Public key to decrypt.
public key to decrypt. Okay, good. And then now they've got, let's say, the symmetric key, right? But actually, what's the problem with that?
Anybody can decrypt it.
Anybody can decrypt it. So Zelda would have also gotten that key, right?
Right.
And then when client resends, now your credit card information, all your money and everything, Zelda can also get it, right? So that didn't work, right? Are you in agreement, all of you?
Yeah, full agreement.
We need to figure out, we're there, we just need to figure out, maybe that's not how we start the process, okay? Maybe we need to think about it in a different way. What if, so what's another suggestion? So we can't send a symmetric key yet, unfortunately, by that approach. So what do we do now?
I mean, you could still do what we said, but before sending it out, you encrypt it a second time, but with Bob's key, just so that way only Bob can decrypt it. Bob's public key, so Bob can decrypt it with his private key. Hope I'm making sense.
Okay. So then and what do we send?
You're talking about the symmetric key. That's like what we're sending, right?
Okay, the symmetric key. So then we took the key again, but this time we use Bob's public, you said, right? Pub?
Well, no, actually, you would still use you would encrypt it using the server's private key. So that way it could only be decrypted using the server's public key, but then you would encrypt it again using Bob's public key.
Right, so yes, but the thing that's providing this, protecting this from Zelda is the fact that you're using Bob's public, correct?
Yeah, because that means only Bob can decrypt it.
Okay, so Bob's public encrypts it. Zelda's here. She can't decrypt it, right? She doesn't have access to Bob's private. Bob receives, you know, the key, uses his private key, and now he can decrypt it, and only he can do it, right?
Right.
Okay, great. Now, let's say that we look at this in reverse, and here, server had to use Bob's public. But what about on the other end, when Bob has to use server's public? So now, Bob has server's public, right? And it's the same thing. Bob is going to send something to the server, right? Whatever it is, some information. So let's say, you know, there's something in here, let's call it plain. So Bob uses, or the browser uses, server's pub, right? And we send it over here, and then now server will use server's private to decrypt it, right? If Zelda looks at it, can she intercept it? Can she read the information?
No, because she doesn't have server's private key.
Exactly. All right, great. So we've established a two-way channel, right? Are you all in agreement that this works? Are there any questions? There is, however, one further problem. Zelda is pretty resourceful. And Zelda comes in and she's going to do a trick. She's going to, what is it? Well, that idea, man in the middle. She creates some kind of channel here. We need it to have servers public, correct?
Yeah.
We need it to have servers public. But while servers public was being sent across the internet, because servers public is in here, in the website of this. So while it was being sent, Zelda takes servers pub and is going to replace it with fake server pub. So she replaces it. So now, because Zelda is a man in the middle, if you will, what came from here is not the same as what arrived here. And I'm only talking about the server pub. The server pub that was sent over here from here is not the same as it was sent here. Do you guys see that? Because she intercepted it and she changed that server key. And if she changes it, she's going to, every time you send something, you know, she's looking at it and then changing it and forwarding it to you. And then she gets something back. She looks at it, she changes it, she forwards it to the next party. Does that make sense, guys?
Yeah.
There's a bit of a problem there. We thought we had solved this on Tuesday, right? We thought for sure we had it. But it turns out the public key itself still needs to be sent across the insecure channel. Do you see the point? So before it was like the symmetric key. Let's call it the block key. Block AES block key, right? That had to be sent, but this is insecure. So then we created a secure channel by using, you know, asymmetric, right? And that means we have pub and private, right? Between, you know, Bob and Alice, right? But this still assumes that Bob gets that public from Alice across how? They would still need to meet in a coffee shop, don't you think? Otherwise, if they sent it across the network, there's a possibility that Alice could intercept it and then become a man in the middle. Do you guys see this problem?
Yeah.
Are there any comments about it? Questions? right? So then we need to add a little piece on top of that, a little piece, a further piece, to ensure that also the key itself, the public key, arrives at its destination securely, unmodified. And that is solved through the certificate authority. All right, the certificate authority provides that final layer of security so that CELDA cannot intercept the public key itself. Imagine how we've gone. You know, we had the symmetric key, and then, okay, to send a symmetric key, we need an asymmetric channel. Okay, but that also needs a public key. Okay, great. Everyone has a public key, but then the public key itself needs to be sent across the network, the internet. Imagine if CELDA is in the middle, a man in the middle, she could replace it. So how then do we finally solve that problem? So that's where the certificate authority comes in. Now the certificate authority is still using all the same primitives that we have used before, just takes it a step further. So how do you think you would take it? So we've gone from here, you know, you understand now, how do we take it to the next level? What do we need to do? What would you recommend? What would you guys recommend? Okay, so let's now think of the problem, Bob and Alice, right? So she's got a public key and a private key, and Bob has a public key and a private key. Now, because we are talking about authentication, intuitively, you could argue, let's call this VeriSign. Simplify things. And VeriSign also has a public key and a private key. You see that? They both have, I mean, VeriSign also has public and a private, just like Bob has public and a private, Alice has public and a private. To secure the communication initially, let's say that Bob is the one that's going to send the message to Alice. So what does Bob need? To send confidentiality, what does Bob need? To Alice. To achieve confidentiality, Bob needs what?
Alice is public.
Alice is public. Very good. So Bob says, I need Alice's public. The problem is Alice needs to send it via the insecure channel. And unfortunately, CELDA is there. She is right there, and she's very good. So what needs to happen? What needs to happen is we need to have a check so that the key that is here is the same as this key once it passes CELDA. So we need to find some way of doing that. So what would you recommend? How do we measure that something hasn't been modified?
Using its hash.
Hash. Great. Right, somebody wrote something? Yep, using a hash, right? So then, okay, let's think about it. Now the public key, do we need to achieve confidentiality on Alice's public key? Is that required? When we send it, when Alice sends Alice's public key to Bob, does that need to be confidential?
No.
No.
No, right? Everybody has it. I mean, CELDA already has that key. The problem is, it's not the problem is that CELDA will intercept that key in transit and will change it. So you can then take Alice's pub, hash it, right? And now you have a hash value that achieves integrity, right? So are we done? Did we solve it?
No.
Why not?
Because if they still intercept it
That's
and
right.
they're able to read the hash, they can just change it and then reevaluate the hash before it gets to Bob.
Perfect. Very good. So the hash does provide integrity, and that's great if there's no CELDA. But Zelda could intercept and do exactly what you just said. She's going to hash it. And so as well, rehash it. And then, you didn't achieve what you wanted. So, let's say you're facing this problem for the very first time ever, right? But you know all these primitives already. You start to build ever more complex crypto systems. What comes to mind then? What could you do? The problem is you can't, you might say, let's go meet at a coffee shop and exchange the keys. But, okay, Bob and Alice might be able to do it because, they're friends and everything. But you, as a user of the internet, you have your browser, just like in PKIa Lab, and you go to Amazon, right? And then you go to, your bank, and you go to Brightspace, and then on, right? Your email, everything that you do. How many different websites do you think you log into every day? Probably lots, right? And then imagine in a year, and they're always changing. You can't, and some of these companies, what if there's a website that just sells something that you really need, but it's in Canada? Are you going to fly to Canada and meet in a coffee shop over there? No, right? So there's got to be another method. So the problem is that you cannot go to 200 different places, 200 different coffee shops to exchange keys. However, you might be able to go to just one. Does that seem more reasonable? That if somebody told you, okay, go to one coffee shop and that's it, problem solved.
And that would be the certificate authority?
That would be the certificate authority, exactly. The certificate authority, such as VeriSign, is literally a company. You have to speak with a person to get that certificate. And in particular, if you're somebody like Amazon, you want that to happen, right? So imagine Amazon literally meets with the certificate authority. They talk about things. VeriSign is what is known as trusted. So the entire security of the internet relies on the fact that VeriSign is trusted and uncompromised. Okay? So if they were compromised, a lot of problems would result from that. So they need to be both trusted, very well respected, highly regulated. People will go to jail, if something happens. But VeriSign then can become that trusted person that is going to vouch for Amazon. Do you guys see that? Do you understand the overall concept?
Yeah.
Okay, so now the question is, how is it that practically VeriSign will vouch for Amazon or for whomever? So we're going back to this idea of the key, right? So going back to the idea of the Alice's public key. This one is not encrypted, it's plain text. This one is the hash. We know what that is. So what needs to happen? What if we took the hash, right? And Alice actually went to a coffee shop and met with VeriSign, right? And then VeriSign basically took her hash of her public key, right? And they did something to that hash. What could they do to that hash? To help provide, to let's just use the generic word vouch, to vouch for Alice's public key, because that's really what we need. We need somebody to vouch for that public key, that it hasn't been modified, right? And the best way to do that is take the hash of the original key and do something to it. This one can be unencrypted. So really, we just need to look at the hash here. So what do you guys think?
Would they add their own set amount of values to the hash?
Who would?
like VeriSign, the certificate authority, would they append their own values to the hash?
Their own values. What if let's think of this scenario. What if VeriSign took its private key and encrypted the hash?
Yeah.
Think about that. Let's just think about that scenario, Now, VeriSign takes this hash. It doesn't even have to take the whole thing because we know a hash is unique, right? Based on Alice's public key, her key can include the key and a whole bunch of information such as, this is Alice's public key. And by the way, she lives at this address. And by the way, she generated it. And by the way, it expires in 2 years and, all kinds of things, right? Doesn't matter. We already learned that whatever text document we have, we can hash it and it's going to be unique, hopefully. That's why we have really good hashing functions. So now that what I'm saying is, what if VeriSign took its private key and hashed it? What happens now? So now we have this element, right? That the hash has somehow been processed by VeriSign's private. What does that achieve even? Because Zelda will have access to VeriSign's public key, correct?
Correct.
So what can she do? If VeriSign signs that hash with VeriSign's private key, and both Bob and Zelda can use VeriSign's public key, they'll be able to see it, right? But what does it accomplish?
Integrity, because they can't, if they change anything of it, the hash is going to be different, not going to match.
Exactly, right? So Zelda now cannot change Alice's public key. She cannot, because if she changes it, the hash will change, and then the hash has now been signed by VeriSign. So when Alice got the key, she didn't get a self-signed public key, or let's say Amazon, right? Instead, they get issued a public key, let's say Alice's public key, but it's signed by VeriSign. Private. You see that? So that's really the combination now. It's not just a public key. It is a public key signed by VeriSign's private key. They don't need to sign the entire thing. They just sign the hash of it because the hash provides the integrity. So now what happens, Zelda, when this key is sent over the channel, Zelda cannot change it. She changes it, she changes the hash, it's gonna decrypt it gibberish, right? So it won't match. What Bob does when he receives this is what? Who can walk me through what Bob would do to ensure that Zelda did not do a man-in-the-middle attack? Guys, what does Bob do now? He receives Alice's or Amazon's public. There's a hash involved in there. Zelda tried to manipulate it, but realized it was signed by the private key of VeriSign, a trusted entity. And Zelda has no access to VeriSign. That's obviously the rule. If Zelda has access to VeriSign, we're in trouble. The whole internet doesn't work. But Zelda does not have access. And so therefore, we got like a little wall there protecting VeriSign. So now what does Bob do?
You would need to confirm the hash, right?
But the hash is encrypted currently.
So decrypt it with VeriSign's public key?
Does Bob have access to VeriSign's public key?
Mm-hmm.
Yes, right? And so once he decrypts it, he's got the hash, and now what does he do? He recomputes the hash, right? So he takes Alice's public, calculates the hash again, compares it to the hash he just decrypted. If they match, what's the outcome?
If
Boom,
they match,
right?
then it's good.
It's good, right? Problem solved. Do you see that, guys? And that public key Now, the assumption was Bob needed to have VeriSign's public, right? Which is public, everyone has. And that's the thing that, because this whole process is automated, it's being done through the browser, then the browser has it in there. You see that? That's the one thing. So all of your browsers have VeriSign's public key in it, period. So your browser has VeriSign's public key. You don't even know that. Then with Amazon and Google and, you know, they might have their own certificate authorities, but I'm just using VeriSign as an example. So they went to a meeting, they sent their lawyers, had a coffee at VeriSign's office, did a bunch of things, and then they ended up with, you know, a public key for their business signed by VeriSign, right? You guys can do this if let's say you create your own website, you go to GoDaddy, for instance, and they're doing the hosting, you just tell them, hey, I also want to buy an SSL certificate. Okay, great, they're going to say. GoDaddy is its own certificate authority, so they're probably in your browser and everyone's browser. So that means GoDaddy's public key is in that browser. And then all that GoDaddy is going to do is they're going to ask you for some money. You're going to pay them. They got your information, your credit card, you know, your address and things like that. They're going to issue, you know, Mary, Alice, whatever, your public key, but they're also going to sign it with their private key. Their public key is in everyone's browsers, and therefore you just achieved the goal. So now we're ready. We've gone from, you know, how to exchange the symmetric key to how to prevent the man-in-the-middle attack. And then now we've completed the cycle, okay? And the key thing, though, is that we need to have a trusted certificate authority. So that was the last missing piece, the last element that we didn't have. And that's what this lab is that you're doing this week, today. It's the PKIa lab, which is about certificate authorities. Are there any questions?
I don't have any.
All right, anyone else? Is this clear for everyone? Okay, great. So it seems like that's that, you know, now once you know that the keys belong to the parties, and once you know everything, all the details, then you can start to then, you know, perform the encryption securely. You can exchange all, you know, then you're going to use the symmetric key, the block cipher encryption key, because of performance. RSA is a little, we'll see in PKIb, RSA takes longer to encrypt and decrypt, and therefore it would be slower. It would slow down your Netflix movies, right? So your Netflix movie would start half an hour later. You don't want that, and so you actually do the confidentiality of your data through public key. But that's it. That's the entire lab. And so what you have to do in this lab is you have to become a certificate, your own certificate authority, you know, so that means you will have to end up adding your own certificate authority information into your Mozilla Firefox browser. And then, you know, everything else, OpenSSL will create the keys for you. And so the PDF is pretty much like a tutorial. You can just follow along. And that's it. That's the lab for this week. As I said, I wanted to give some time, so I didn't want to just lecture the whole period. So now I'm just going to open the floor to questions of this lab, previous labs, whatever you're having trouble with. If you want to share your screen, go ahead. If you feel that everything is clear, well, you can sign off. I'm going to stop the video at this time and just leave it open for questions.
I have a quick question about the lab that's due tonight.
Go ahead, please.
Because there is a coding portion, do you want us to just have screenshots of our code in the Word doc, or do you want us to actually send the Python
You don't
file?
have to send me the Python. No, just have screenshots is fine. I do need to see a screenshot of it running though. However you solved it, I need to see that screenshot.
Yeah,
And
the
you-
execution.
Yeah, because of that, yes, of it running, yes, the execution. Just a screenshot. Remember, it's if you think your screenshot is convincing, you know, I just need some evidence that you did it, right? So I need to know something. So, and you usually know, right? You usually know, okay, I did it, and here's the screenshot. So provide that for me. Because of that script, I usually leave it. I give you this time today. So if there's any questions, go ahead and ask.
Thank you for the answer, though. Thank you.
No problem. So as I said, I'll start, you know, your homework assignment was submitted last Thursday. So the first one, I will start looking at it this week. So hopefully by next Monday, you'll have the grade for homework 1. Homework 2, you're submitting tonight, correct? Am I wrong about that?
Yeah, I believe so.
Right, so you're submitting that tonight, due tonight. All right, so go ahead. So I'm going to stop. I don't usually like to go over solutions in the video, right? So I'm just going to stop, pause recording, but I'm still here. And if you have any questions, go ahead and ask. All right, guys, I have posted the link for the homework assignment, PKIa, with the instructions. So you should be able to see that on Brightspace. So, you know, make sure you work on your assignment, submit the one that's due tonight, and then start working on PKIa. On Tuesday, we will continue with asymmetric encryption and just continue to discuss and build more complex cryptographic techniques. All right. So we will stop here for today, and I will see you guys on Tuesday. Have a good weekend.
Thanks, you too.